Factors affecting absorption bands. Here are the factors that affects these stretching and bending vibrations. The intensity of the absorption band is going to depend on the polarity of the bond and therefore the dipole moment, and the number of bonds that's present in the molecule, and the concentration of the sample that is used for taking the IR spectrum. And the position of the absorption bands is going to depend on the size of the atoms and the bond order, which is basically the number of bonds that's between the two atoms. And both the shape and the position of the absorption band is going to be affected by electron delocalization by resonance, inductive electron withdrawal, and also hydrogen bonding. Let's take a look into each one of these in detail. Intensity of the absorption bands. Let's say you're going to stretch a bond that exists between X and Y. Now, whenever you stretch the bond, it's definitely going to have an increase in the bond length, right? So with the increase in its bond length, you are definitely going to experience an increase in the dipole moment. So the dipole moment is also going to increase. Now, the most important thing here is the intensity of the absorption band is going to depend on the size of the change in the dipole moment. Greater the dipole moment, greater will be the intensity of the absorption band. Let's do this with an example. Let's take a look into the C double bond O and C double bond C. Now, between these two, when you take a look into the stretching frequencies for these two types of bonds, you can see that they are about the same, right? If that's going to be the case, how can we differentiate both of these two different types of bonds? That is by intensity. So obviously, you can see that the C double bond C has a lower intensity than the C double bond O. This is because the dipole moment of C double bond O is much greater than the dipole moment of C double bond C. So this has a greater dipole moment, and therefore the intensity of this absorption band is really strong compared to the C double bond C. Also, when you compare the intensities of OH bond with NH and CH, you can definitely say that the OH bond is the one that's going to be more intense because this is the most polar bond. So between OH, NH, and CH, this is the bond which is going to have greater dipole moment, and this one is least polar, and therefore this is going to be less intense. The absorption band that corresponds to the CH is going to be less intense. So greater dipole moment and then greater polarity of the bond, stronger would be the intensity of the absorption band. The intensity of the absorption bands is also going to be affected by the number of bonds present in the molecule. Greater the number of bonds, greater will be the intensity. Let's take a look into the structure of octyl iodide. Here you can see that there is a total of 17 carbon-hydrogen bonds. But in the case of methyl iodide, there is only 3 CH bonds. Now between these two, obviously this is definitely going to produce a very strong, intense absorption band for CH compared to this one. And the third one is the concentration of the sample. When you have a greater concentrated sample, then obviously it is definitely going to, more molecules are going to absorb the radiation, and therefore it is going to produce more intense absorption bands. The position of the absorption bands, basically the frequency of the stretching vibrations, is going to depend on two things. One is the strength of the bond, and the other one is the masses of the atoms bonded to each other. So basically, it's going to be dependent on the size of the atoms and as well as the bond order. We can calculate the approximate wave number of stretching vibration using this equation called as the Hooke's law, where nu bar is basically the wave number and F is force constant. It is a measure for the strength of the bond, and M1 and M2 are going to be masses of the atoms. From this equation, it's clear that wave number is directly proportional to force constant, whereas it is inversely proportional to the masses. So when you have lighter atoms and stronger bonds, we'll definitely be seeing a larger wave number. This can be seen from the stretching frequencies of these bonds right here. So let's take an example of CH and CD bond. So now between CH and CD, we can obviously see that CH has a higher frequency or a higher wave number. Now why? What is the reason behind it? So between the hydrogen and deuterium, obviously the lighter atom would be hydrogen. So this is a lighter atom, whereas this one right here is comparatively heavier, right? A lighter atom is generally going to be tightly held by the other atom. So therefore, there is going to be a strong bond. A strong bond and a lighter atom is going to result in higher wave number. And that is the reason why we see a higher wave number for CH when compared to CD. And the same thing goes for even these two bonds right here. So between hydrogen, deuterium, oxygen, and chlorine, you can see that chlorine is going to be a heavier atom, and therefore it is not tightly held by the carbon. This bond right here is a weaker bond relatively, right? And therefore it's going to stretch at a lower frequency. Whereas this bond right here is a stronger bond, and therefore you see a higher frequency for it. The bond order is going to be directly proportional to the wave number. So greater the bond order, greater would be the stretching frequency. So obviously it takes more energy to stretch a double bond than a single bond. And similarly, it takes more energy to stretch a triple bond than double bond. So here you can see that there are different carbon-nitrogen bonds. The triple bond has a higher frequency of 2200 centimeter inverse because it's going to take more energy to stretch this triple bond, but it's going to take only less energy to stretch this carbon-nitrogen single bond. And similarly, when you take a look into the carbon-carbon triple bond and the carbon-carbon double bond, you can see that the carbon-carbon double bond is at a lower frequency, while the carbon-carbon triple bond is at a higher frequency. And the same thing goes for even the carbon-oxygen double bond and single bonds. So the carbon-oxygen double bond is at a higher frequency, whereas the single bond is at a lower frequency. So greater the bond order, greater will be the stretching frequency. Now the last thing is that the shape and the position of the absorption bands is also going to be affected by electron delocalization by resonance, inductive electron withdrawal, and hydrogen bonding. Let's now take a look into how the electron delocalization by resonance is going to affect the frequency of the stretching vibration. Now here we have two different compounds. We have 2-pentanone and 2-cyclohexanone. Now both of these compounds have got carbonyl group. Here is a carbonyl group, and this also have got carbonyl group. While 2-pentanone stretches at 1720 centimeter inverse, this 2-cyclohexanone stretches at relatively lower frequency of 1680 centimeter inverse. Now what is the difference? Although both of them have exactly the same carbonyl group, why 2-cyclohexanone stretches at a lower frequency? Here in 2-pentanone, this carbonyl group right here, this carbon-oxygen bond right here is purely double bond. But in 2-cyclohexanone, that's not the case. Because these two double bonds are conjugated with each other, what's going to happen is there will be another resonance contributor for this molecule. So where these electrons will hop in, and the pi bond is going to break, and it's going to move on to oxygen to give this other resonance contributor. Now you can see in this resonance contributor there is a carbon-oxygen single bond. On the whole, what we can say is this carbon-oxygen bond is not going to be purely double bond. Instead, it's going to be a mixture of double and single bond. So we should say that there is at least some single bond character, right? So we have talked earlier that the bond order is going to affect the frequency of these stretching vibrations. So greater the bond order, greater would be the stretching frequency. Here we only have a double bond, which is going to be stronger, right? And therefore it is going to have a higher frequency. So this one right here is higher frequency compared to what we have in the case of 2-cyclohexanone. But here, since we have both double bond and single bond character, the strength of the bond is weaker, or bond order is going to be slightly less, and because of which it is going to stretch at a lower frequency. So this one at lower frequency. So the electron delocalization have affected the bond order, which in turn has affected the frequency of the stretching vibrations. According to what we have talked now, the electron donation by resonance is going to decrease the frequency of the carbon-oxygen double bond. So basically, it's going to be between a double bond and a single bond. But how the inductive electron withdrawal is going to affect the frequency of the stretching vibrations? Inductive electron withdrawal is going to increase the frequency of the carbon-oxygen double bond. Let's see how. Let's say this is your carbonyl compound, okay, and Z is an electronegative atom. What is the inductive electron withdrawal? Inductive electron withdrawal is the movement of the electrons along the sigma bond. So let's say that you have some electrons, some lone pairs of electrons on this oxygen. So these electrons are going to come in, okay, and it's going to strengthen the carbon oxygen double bond, and some of the electrons is going to go on to this electronegative atom. Because it is strengthening this carbon oxygen double bond, it's definitely going to stretch at a higher frequency. So inductive electron withdrawal is going to increase the frequency because it increases the bond order slightly. Okay. So while the inductive electron withdrawal is going to increase the carbon oxygen double bond stretching frequency, the electron donation is going to decrease the carbon oxygen stretching frequency. Let's take two different compounds which have carbonyl groups in them. Let's take an ester. Let's also take an amide. Now, in these two compounds, we are going to find out the predominant effect of each of these electronegative atoms, right? So let's first see what is going to happen if there is electron donated by resonance. We needed to first draw the resonance contributor. Let's say that these electrons are shifted in, okay? Then it's going to result in this resonance contributor, which puts a positive charge on this oxygen. Let's also do the same thing for the amide. For the amide, again, you have these lone pairs of electrons present on nitrogen. These electrons are going to hop in here, and this is going to go. These electrons will be thrusted onto oxygen to form the resonance contributor. Now, between these two resonance contributors, which one would be a reasonable contributor? Obviously, it would be this one. Because here, in the case of ester, you're trying to put the positive charge on the atom, which is most electronegative. Nitrogen is able to accommodate this positive charge much better than the oxygen. So the predominant effect of nitrogen in the case of amide would be electron donation by resonance. So here, in amide, there is electron donation by resonance. But in the case of ester, since this positive charge, since oxygen is not able to handle this positive charge well, the predominant effect in ester would be inductive electron withdrawal, where these electrons are going to come in and strengthen this double bond, right? So this would be inductive electron withdrawal. Now let's see what's going to happen to the stretching frequencies of the carbonyl group in each one of these. Let's take a look into the IR spectrum. From the IR spectrum, we can see that the carbonyl group for the ester is at 1740 centimeter inverse. And for the amide, it is at this place right here is at 1660 centimeter inverse. You can see the difference in the stretching frequencies of the two carbonyl groups in these two different compounds is because of the two different effects, right? While the inductive electron withdrawal is going to strengthen the carbon-oxygen double bond, making the carbon-oxygen double bond to stretch at a higher frequency, the electron donation by resonance is going to weaken the carbon-oxygen bond, thereby having the stretching vibration at a lower frequency. I strongly suggest using this table for the IR absorptions, where you can see separate stretchings for the separate carbon stretchings for the different functional groups.